Hi everyone. So I'm going to do this discussion online. Obviously, it seems there's like nobody right now in the discussion room, so I'm just going to go over it and then you will be able to see it online through the video. So this discussion has two problems. The first one is about complementary slackness and KKT conditions. So the first one is trying to have you solve like a really easy problem, kind of straightforward, just to make you understand like what is KKT conditions or what are KKT conditions. The second one is using a program that we have solved using drawings, which might be a little bit harder, where you plug like different objective functions here. And this should kind of give you some tools you can use or ways to use KKT conditions to find solution of optimization problems. So let's go over like the first problem. So here we want to minimize x squared given that x should be between 1 and 2. So those are feasible points. So this is kind of straightforward. What is the solution? The solution is here. So the minimization of x squared with x between like 1 and 2 is just like x star is equal to 1. But now let's try to see how we can use KKT conditions and duality to find the same thing. And just to make sure that everybody understands, you can do like the following. X greater than 1 is equivalent to or implies that x squared is greater or equal than 1, which means that the minimization of x squared such that x greater than 1 is greater or equal than 1, and which is actually equal for x star is equal to 1. So this would be the way to show that the minimum of this problem is obtained for x star is equal to 1 if you don't know anything about optimization. So the first question asks you about the latter conditions. So first, you know that your problem is convex because x gives x squared is convex. And then x greater than 1 and x smaller than 1 define a convex set. And for the latter conditions to hold, you need to have at least one point in the relative interior of your feasible sets. So here if you have like x is equal to 1.5, you have 1.5 which is strictly greater than 1 and 1.5 which is strictly smaller than 2. So the relative interior of the feasible set is not empty. So the latter conditions hold. So this here shows that the problem is convex. And because the latter condition holds, we have strong duality. Now, as you recall from previous discussions, we actually don't like constraints in optimization because it does not allow us to set the gradient to be equal to 0. So what we do to remove constraints is we set the functions to be equal to the function on the feasible set and equal to plus infinity otherwise. So this function here is equal to the function itself if x is feasible and plus infinity otherwise. And the set of feasible points is just the set of points such that x is greater than 1 and smaller than 2. And you might remember that this function, you can also express it as, you can also express these functions, the f tilde, as the maximum over lambda 1, lambda 2 greater than 0 of the Lagrangian. So the Lagrangian is x squared plus lambda 1, 1 minus x plus lambda 2, 2 minus x, sorry, x minus 2. And now the function I draw here in red, f tilde, this is just equal to the maximum over lambda 1 greater than 0 and lambda 2 greater than 0 of the Lagrangian of x. And this, I think you have shown it. And so now, just like to remember, like now your problem, P star, could be expressed as the mean over the max of the Lagrangian. So here you are happy because you do not have any constraint anymore on x. Here there is no constraint on x, but you are not happy because you have to solve like another maximization problem before, and this maximization problem will give you some constraint on x. So what you want to do to be able like to take the derivative of the Lagrangian with respect to x to solve this problem is you want to switch the mean and the max. But as you know, because of weak duality, if you switch the mean and the max, you will not have the same results. So this is the dual problem. T star is equal to the max of the mean over x of Lx lambda 1, lambda 2, lambda 1 greater than 0, lambda 2 greater than 0. And this is not equal to P star, that's kind of the issue. But it's smaller or equal than P star. But this is easy to solve because you can solve this by just setting the gradient to 0. So if you fixed lambda 1 and lambda 2, and then you show that the Lagrangian is convex and differentiable with respect to x, then you can solve this problem with a fixed lambda 1 and lambda 2 by just setting the gradient of the Lagrangian with respect to x to be equal to 0. And you will find an optimal point that depends on the lambda 1 and lambda 2 you have fixed. So you can plug in this x star in the Lagrangian and then solve the dual problem. And this condition is the stationary conditions of the KKT condition. And this is 2x plus or minus, sorry, minus lambda 1 plus lambda 2 is equal to 0. And then, so what you know is, so you want this here, like this thing here, to be equal to x star squared at the optimum. And you know that this is strictly greater than 0, and this is strictly greater than 0 for feasible points. So at the optimal point, you need to have like this to be equal to 0, and this equal to 0 at optimum point. So this is complementary slackness. Okay, and now if you want your optimal point, you still need the optimal point to be feasible. So here you can see that x cannot be equal to 1 and to 2 at the same time. So you need at least lambda 1 or lambda 2 to be equal to 0. Maybe both are equal to 0 and x is not equal to 1 or not equal to 2. But that's actually not the case. So if both are equal to 0, x is equal to 0 because of this condition, and x is not feasible. So they cannot both be equal to 0. So you have to have at least one equal to 0. You have to have one equal to 0. So either like lambda 1 is equal to 0, either lambda 2 is equal to 0. And so if lambda 2 is equal to 0, x is equal to 1, and lambda 1 is equal to 2. So this works. But if lambda 1 is equal to 0, then x is equal to 2, and lambda 2 is equal to minus 4. So this does not work. So the solution is x star is equal to 1, lambda 1 star is equal to 2, and lambda 2 star is equal to 0. So I'll let you do it maybe again by yourself to make sure that you understand why this is the solution. And feel free to ask any question on Piazza if this is not clear, or to just watch the video again. So question D is just kind of asking you about complementary slackness. So you just have lambda 1 star is equal to 0 if x star is equal to 1, or lambda 2 star is equal to 0. Sorry. So if lambda1 star is equal to 0, then lambda x star is equal to 2. And if lambda2 star is equal to 0, then x star is equal to 1. So you cannot have like lambda1 and lambda2 star cannot be. No, sorry, I think I said something wrong. Sorry. So if lambda1 star is not equal to 0, then x star is equal to 1. And if lambda2 is not equal to 0, then x1 is equal to 2. So here, if lambda1 is not equal to 0, then x is equal to 1. And same thing here, just by complementary slackness. And as I told you, for feasible points, this is the Lagrangian to be only equal to x squared. So you want this to be equal to 0 and this to be equal to 0. And that's complementary slackness. So it's kind of easy to see that the KKT conditions are necessary for optimality. Something which is nice here is that the KKT conditions gives you only 1 point. And you know that for a convex problem, you have one optimal point if like the minimum is obtained. So here, you know that this point, the point that you have found, is actually the solution. And for convex problem with Slater conditions, I guess, KKT conditions are sufficient. So something that you can see here, which is kind of funny, is lambda1 star is equal to 2 and lambda2 star is equal to 0. And now if I draw x squared as a function of x between like 1 and 2, the minimum is here. If I say, okay, x is smaller than 2 plus epsilon and x is greater than 1 plus epsilon. So epsilon 1 here, epsilon 2 here. Or let me even do it in the other way. Epsilon 2 here, epsilon 1 here. So if I move a little bit the epsilon 2 here, I put my new constraint maybe here, 2 plus epsilon 2. So I will reduce my feasible set or change my feasible set around 2. It will not change the optimal point. And this is actually what you can read when you see that the dual variable is equal to 0. So if the dual variable is equal to 0, it means that the constraint is not active. So by changing it a little bit, you will not change the optimal point. Not active because lambda2 star is equal to 0. But now if you move a little bit the constraint at x should be greater than 1. If you move it here or here, then it will move your optimal point. And here's something which is funny. It will actually move your optimal point by epsilon times the slope of the tangent at 1. And the tangent of x, the slope of the tangent of x squared at 1 is actually equal to 2. And here you can see that lambda 1 star is equal to 2, which is actually the slope of the tangent of x squared at x star is equal to 1. Then you have like some kind of, so if you move a little bit your constraints, then your new optimal value is equal to your old optimal value plus lambda 1 star times epsilon 1. And this is called sensitivity analysis using dual variable. So this, you have not done it in class right now, but some of you might understand what this means. So when I have like this minimization over my Lagrangian, if I move a little bit my constraints here, it will move my optimal point by like the factor lambda if the constraint is active. And this, I think it's well explained in the Boyd's book, and you might do some homework on it. So now let's find like the dual function. So we have the Lagrangian. So here we can find the minimum of the Lagrangian with respect to x by just setting the gradient to be equal to 0. So which is the stationary condition of the KKT condition. Which just gives you that x is equal to lambda 1 minus lambda 2 divided by 2. And if you plug this x in the Lagrangian, you will find the dual function, which is equal to minus lambda 2 minus lambda 1 squared divided by 4 plus lambda 1 minus 2 lambda 2. This I let you do the calculus on your own. Okay? Sorry about that. I have like an issue with my internet connection. So what we have done so far is we found the dual function. And this dual function, now we want to solve the maximization of the dual function. Such that lambda1 and lambda2 are greater than 0. So what we can do is, sorry, I think I did some mistakes so far. So what we can do is try to set the gradient with respect to lambda1 and to lambda2 to be equal to 0. And this will give us, so I think the first one is lambda2 minus lambda1 divided by 2 plus 1. And the second one is minus lambda2 minus lambda1 divided by 2 minus 2. So this should be equal to 0. So both should be equal to 0. And this will give us I think this you will not be able to find a solution where lambda1 and lambda2 are both equal to 0. So what you will do is, instead of setting the gradient to be equal to 0, if you cannot set the gradient to be equal to 0, it means that the optimal point is achieved at the constraint. So either lambda1 is equal to 0 or lambda2 is equal to 0. And this we can do it. So if lambda1 is equal to 0, then you just have j of lambda2 is equal to minus lambda2 squared divided by 4 minus 2 lambda2. And if you want to maximize this, you will actually find lambda2 is equal to 0. And j is equal to 0. And if lambda2 is equal to 0, you have j of lambda1 be equal to minus lambda1 divided by 4 lambda1 squared plus lambda1. And if you want to minimize this with respect to lambda1, you will find that minus lambda1 divided by 2 plus 1 is equal to 0. So lambda1 is equal to 2. And j of lambda1 is equal to 1. J of lambda2 is equal to 0. So this case, j of lambda is greater than this case. So this is the solution, because you want to find the solution that maximize j of lambda1, lambda2. So the solution is just lambda1 star is equal to 0, lambda 2 star is equal to 2, and j of lambda 1, lambda 2 is equal to 1. And here you have like, so here you kind of know that this would be the solution because of strong duality. But here you have also like, we have explicitly shown that both are equal. So the dual problem and the primal problem. But this you already know it because you have the Slater conditions, but we wanted to do it. Okay, so that's what you should know about exercise 1. And now let's do exercise 2. So exercise 2, we have already kind of solved it using drawings. So you have like this set of points, which are the feasible points. And here, if I draw them on the figures, like this one is x2, next one is greater than 1. This one is x2 is greater than 0. And you have the two other ones. And this is such that the set of feasible points is like all those points are the feasible points. So you want to solve like this problem. So you have like a set of feasible points, and you want to find on this set of feasible points the minimum of a function, and we'll plug in different functions. So first you can express the Lagrangian. So you have four constraints. So you will have 4 dual variables. And then, so here, like, remember, like this Lagrangian is a way to express your problem without any constraints. So if I define this function f tilde, which is the maximum of the Lagrangian with respect to lambda 1, lambda 2, lambda 3, and lambda 4, all greater than 0, this would be equal to f of x1, x2 in the feasible points, in the feasible sets, and plus infinity otherwise. So this function, you can represent it as on the feasible set, it's equal to the function and outside it's equal to plus infinity. So that's the main idea of the Lagrangian, is to remove the constraints, and then when you swap the min and the max, then you can take the derivative with respect to the Lagrangian, of the Lagrangian with respect to x1, x2 if the Lagrangian with respect to x1, x2 is differentiable. So now let's try to solve some of those problems using like KKTs and what we know about like duality, KKT conditions, and convex problems. So something you know is, you know that at the optimal point, you need your Lagrangian to be equal to your function. So this should be equal to the Lagrangian at optimum point. And you also know like those things that we add to the Lagrangian are greater than 0 if x1, x2 are feasible and lambda 1 is greater than 0. So this means that at the optimal point, if you want your Lagrangian to be equal to your function, you need to have all of those to be equal to 0, which is complementary slackness. So complementary slackness kind of gives you that either the constraint is active, so either the constraint is active or either the dual variable associated to the constraint is equal to 0. And so this is nice because when you have the drawing, so for example, like if I want to solve this problem, so I want to solve this problem where like f of x1, x2 is equal to x1 plus x2. I know here that I can draw the level sets of the function. So this here is just x1 plus x2 is equal to a constant. So this is the set of points x1, x2, such that x1 plus x2 is equal to a constant. So this is the level set of f x1, x2 is equal to x1 plus x2. So I think using the drawing last time, what we did is we tried to find the level sets. We tried to minimize the value of the level sets such that you still have one point in the feasible region. And so at the end, you will find this level set. This is the lowest level set with an empty intersection with the set of feasible points. So you have like a level set of your function. So you fix like the value of the level set. And then you just try to minimize this value such that you still have like one point at least in like the feasible sets. So here, for example, from this C, we go to this C star with this color. And this you just go from like this level set to this level set. And this level set is the lowest level set with an empty intersection with the set of feasible points. And this gives you that the optimal point is here. And I think for LPs, what you do is you can express this as 1, 1, x1, x2. And this is the vector 1, 1. The level set should be orthogonal to the vector 1, 1. So you just find the 1 you just like go over like all those different lines orthogonal to the vector 1, 1 or hyperplane, and then you decrease the value of the level sets until you reach a corner of your feasible set to solve like LPs, so linear programs. This you will see it probably in next lectures. And then once you are at this corner, you know that you have only like one point for the intersection between your level sets and your feasible points. And so this is the lowest level set with an empty intersection with the set of feasible points. So you have like your optimal point here. So I'm kind of sorry if this is not clear, and you will probably like understand it better like when you will do linear programs. So something which is nice by doing this is that you can understand that here you have two constraints active. You have this one is active. So using drawings gives that probably this is active, and probably the other one, so this one is also active. And this gives you that also probably like this one, x1 greater than 0 and x2 greater than 0 are not active. So which means that lambda 3 is equal to 0 and lambda 4 is equal to 0. So this is what you assume. So using the drawing, you can assume this. So what you can do is you can assume lambda 3 is equal to 0, lambda 4 is equal to 0. So now you have the Lagrangian is just x1 plus x2 plus lambda 1, 1 minus 2x1 minus x3 plus lambda 2, 1 minus x1 minus 3 x2. Then you can find the KKT conditions. So the derivative of the Lagrangian with respect to x. So sorry. So here, what you see is you see that your Lagrangian is differentiable with respect to x and is convex with respect to x. So to find the minimum of the Lagrangian with respect to x, you can set the gradient of the Lagrangian with respect to x to be equal to 0. And this will give you 1 minus 2 lambda 1 minus lambda 2 and 1 minus lambda 1 minus 3 lambda 2 is equal to 0. And so once you have this will give you that lambda 1 is equal to 2 divided by 5 and lambda 2 is equal to 1 divided by 5. And this is good because they are both like greater or equal than 0. So which is like what you want for dual feasibility. And then this, if you plug those values, so lambda 1, lambda 2, and lambda 3 and lambda 4 in your Lagrangian. Sorry. So if this is, so because you have this, so lambda 1 and lambda 2 are strictly greater than 0, then you know that the constraints are active, which gives that x1 is equal to 2 divided by 5 and x2 is equal to 1 divided by 5. And so you have like this set of points that satisfies the KKT conditions. So meaning that for these lambdas, the Lagrangian with respect to x is equal to 0. And then the two constraints associated with lambda 3 and lambda 4 are not active. And the two constraints associated with lambda 1 and lambda 2 are active, which is complementary slackness. Then all the lambdas are greater or equal than 0, which is dual feasibility. And then you can see that x1 and x2 are also feasible points, which is primal feasibility. So KKT conditions, just to make sure, is like you have primal feasibility, then you have like dual feasibility, then you have complementary slackness, and then you have stationarity conditions. And so those points satisfy all those things. So for two, here we have shown that the minimization of this problem is equal to minus infinity. So this we have shown in discussion 5, I think. And this we do not need KKT to show that this is equal to minus infinity. So let me do like the KKT conditions again for D and for E, just to make sure you have like you understand like how to use like the KKT conditions. So for D, here you see that the level sets are orthogonal to the x-axis. So if you want to minimize the level sets, you will go this way until the intersection And the last one you can find where the intersection between the level set and the feasible points is not empty would be this one here. And so your set of, so you might assume, we might guess that the set of optimal points are those points. But this is using drawings and does not show that this is correct. So you really need to use KKT conditions to show that this is correct, showing that all those points here satisfies the KKT conditions. So here, what we can assume is that lambda 1 is equal to 0, lambda 2 is equal to 0, and actually here we do not use KKT condition either for this one, sorry. Here there's like an easier way to do it. So x1 greater than 0. So this is one of the constraints, imply that f of x1, x2 equal to x1 is greater than 0. This is constraints. And this is just like an objective function. And now if you want it to be equal to 0, this is equivalent to x1 is equal to 0. And now if you want x to be feasible, and x1 to be equal to 0, this means that x2 should be greater than 1. So here you have solved already like you have already solved like the minimization problem. So all those things gives you that the minimization of x1 such that x is feasible is equal to 0, and the set of feasible points, the set of solutions is just all the x2, sorry, the 0 x2 such that x2 is greater than 1. So you do not need KKT conditions for problem D. And then problem E is a little bit harder than what we have done so far. And I really suggest you do it, you try to redo like those different problems by yourself. So if you want to use the Lagrangian of this function, you will see that this is the max between x1 and x2, plus like the other terms. So the other terms are the terms are like those terms here. But here you have like, this is not differentiable with respect to x. With respect to x. With respect to x. So this you cannot use, so therefore you cannot use KKT. And that's a big issue. So the way to solve this problem is to actually formulate it as an equivalent problem where you can find a Lagrangian with respect to your variables, to your primal variables, which is differentiable. And here you can do the following: is mean of the max of x1, x2, such that x is in the feasible sets. This is also equivalent to the mean of x, t, t is greater than x1, t is greater than x2, and x is a feasible point. And so now if I have like this problem, I can express the Lagrangian of this problem, which is L of t x lambda, which is t. So this is like the objective function, plus all the previous constraints. So lambda 1 minus 2x1 minus x2 plus lambda 2 so 1 minus x1 minus 3x2 minus lambda 3 x1 minus lambda 4 x2. And then you have like two new constraints. Those two that you have to add. So plus lambda 5 x1 minus t plus lambda 6 x2 minus t. And now this Lagrangian is differentiable. With respect to your new primal variables, which is t, x1, x2. So now let me like solve this one, and then I will end the discussion. And I'm not going to solve f, so you're going to solve it by yourself. Solve it by yourself and look at the solution. So for E, here are the level sets. So what you expect from the drawing, is that the constraints x1 greater than 0 and x2 greater than 0 are not active. So lambda 3 is equal to 0, lambda 4 is equal to 0. And then you also expect that you will arrive at this point here. So there's like this constraint would not be active. So you can expect that lambda 2 is equal to 0. And here you are on the line where like x1 is equal to x2, which means that you expect that x1 is equal to x2. And this you can only have it if the two constraints x1 greater than t and x2 greater than t are active. And you expect that the last one is also active, so 2x1 plus x2 is equal to 1. So this is what you expect from the drawing. And if you solve this, we'll find x1 is equal to x2 is equal to t is equal to 1 divided by 3. And so let me like do that. So here we expect x1 equal x2 equal at t 1/3, and then lambda 2 is equal to 0 equal lambda 3 equal lambda 4. Then if we do the Lagrangian with respect to t and x, the derivative of the Lagrangian with respect to t and x to be equal to 0, this will give us that lambda 1 is equal to lambda 5 is equal to lambda 6, and they will all be equal to 1/3. And here we would have the KKT, and with those values, we can check that the KKT conditions are true. So we can check primal feasibility, dual feasibility, complementary slackness, and stationary condition. So just to summarize, what you do is you look at the problem, then you formulate the Lagrangian. You hope that L is convex and diff with respect to X. If it's not the case, then maybe reformulate. And if it's convex and diff, you set the Lagrangian to be equal to 0, which will give you some conditions on the X and the lambdas. And then you add the complementary slackness to find X star and lambda star feasible. And then once this is done, check again that those satisfies the KKT. So that's how you will do it. Okay, so I hope it was clear. There's the discussion solutions online, and you can ask me many questions, or you can ask many questions on Piazza, and you can watch again the lecture, and maybe like if there's like anything which is not clear, I can maybe try to do like a new discussion, like a new recording on Zoom, or just like answering some questions on Piazza. Okay, thank you a lot for your attention, and see you soon. Take care of you and be safe.